is usually for getting into a math major, or maybe just something you'll pick up if you're a math enthusiast, or, you know, from a math club or something like that. So it would make sense if some of this wording is not familiar to you, unless you are a math major or you've graduated or whatever. But just in general, like for typical math classes in school, this is not usually taught. So I will try to explain everything, though. I think conceptually it's pretty straightforward. Modular arithmetic is just all about division and remainders. And for today, I'm just going to be applying the Chinese Remainder Theorem. We're not going to prove it or get too theoretical here. It's going to be more algorithmic, I would say. Algorithmic. So I'm just going to focus more on calculations. This question was borrowed from like an old MIT paper. I have not looked at this stuff in so long, so I think this will just be really fun to refresh, and hopefully we get an answer. I actually didn't even check that, but the cool thing is this is one of those exercises where if we actually get a solution, we can actually check it. So hopefully we get something, and I find that for discrete math, it's just easier to check, which I find to be very satisfying. So hopefully we get something, but let's just focus on the process, and let's look at this notation first, okay? Are you ready? Okay, so let's start with what these mean in the first place. Okay, so this is a system of congruences, just like a system of equations in algebra. Your goal is to find the values of your variables that satisfy all 3, 2, 4, however many equations you have at the same time. So it's the same idea here. I have just one variable, x. I'm trying to find x that satisfies all 3, and it might be a specific value. In this case, with modular mathematics, you usually have like a class of solutions. So in this case, that's what we're doing, and we want, for instance, this first line says that x is going to be congruent to 1 mod 3. So that's what this weird looking equal sign is. It's equals, but it just shows congruency, which means that if x is congruent to 1 mod 3, I think I have a video on basic modular arithmetic, but this just basically means if I take my number and I divide it by 3, the remainder is going to be 1. So note that there's not just one solution to this congruency statement. There's going to be infinitely many. The nature of modular arithmetic is that it's circular. So, for instance, if I have 1 is congruent to 1 because if I divide it by 3, 3 goes into 1 0 whole times, and that just leaves me with the remainder of 1. It's kind of like the base case. But if I look at 4, 4 divided by 3 is 1, so 3 goes into 4 1 whole time, but then there's a remainder of 1. Same for 7. 3 goes into 7 twice, which gives me 6, and that gives me a remainder of 1. So it's like a whole class of numbers that would satisfy this congruency statement, okay? So note that we don't actually really care how many times, it's just kind of this circular nature, and you can basically just divide out multiples of this mod number to look at this remainder here. So that's the gist of it, but here we have x is going to be congruent to mod 5. So if I have my number and I divide it by 5, So we're actually keeping track of remainders instead of having decimals or fractions to represent the, last little piece. We're actually keeping track of the remainders, and for now not really caring about how many times this number goes into it. So we're looking for a number that satisfies all three of these conditions, or a class of numbers. So that's where the Chinese Remainder Theorem comes in handy. The main condition though, like the main condition for us to be able to use it is that these what's the word, like the moduli, I guess, but that these numbers are relatively prime or co-prime. So any two of them, so therefore all three. And what that means is just that the only common factor between all three, or between any two of the three, and therefore all three, is going to be 1. And that's the only way we can actually use this Chinese Remainder Theorem. So in this case, 3, 5, and 7 are prime numbers themselves, which means that their only factors are 1 and the number itself. So for 3 it's 1 and 3, for 5 it's 1 and 5, for 7 it's 1 and 7. So by default, the only common factor between them is going to be 1. So we're good to go there, but it's important to check to make sure. So what we're going to do here is I'm just going to try to get a solution. I'm not really sure how I'm going to write this out, but there are several different calculations to make. So the first thing is I am going to multiply 3, 5, and 7. So I'll just call this a capital N here. So 3 times 5 times 7. Because, let me see, this is 15, so 105, right? Let's check that. Let's check that. 3 times 5 times 7 equals, yes, 105. Okay, so the reason I do that is because our solution is going to be mod 105. Okay, so we are not going to be repeating any factors. That's kind of why we need to make sure that there are no other common factors besides 1. So we're going to start with this 105. And then, how do I write this out? So I guess I'll start with looking at the congruence conditions, right? So I'll write 1, 2, and 3. And, so there are like a few calculations to make. The general idea is that we're going to be multiplying a bunch of stuff and then like do it for each number, and then we're going to add those products together to get our answer. So I guess it'll kind of be like a table. So I'll start with 1, 2, 3, which corresponded to these congruence conditions here. So if there were different numbers, you can just write those. Then the next thing I'm going to do is there's a particular value here that corresponds to 1, and it's going to be this 105, which is 3 times 5 times 7. And then for this one that corresponds to 1, I'm going to divide it by 3. So the thing is, 105 is 3 times 5 times 7. So when I divide that by 3, I'm just left with 5 times 7, which is 35. So the 3's basically cancel. So for the next number that I'm going to be calculating that correspond to, 1, 2, and 3 each line, it ends up basically being the other two numbers multiplied together. So 3 times 7 is 21. And for the last line, the one that corresponds to 3, it's just going to be 3 times 5. So it's like multiplying the other two moduli that are not the one that we're looking at. And that just works out simply because we are taking the full product of the 3 and dividing by the one that we're looking at. as just kind of trial and error. You can multiply by 2 and you would get 70. I know 1 doesn't work because if you divide by 3, you're going to get a remainder of 2 because this would be 33 with a remainder of 2. So that's not 1. But if you multiply by 2, you get 70. And then if you divide by 3, that would be 69, and then a remainder of 1, right, for 70. So y equals 2 would be your inverse. So you can do that by hand. So the inverse is 2 here. You can do that by hand. That wasn't so bad. But you could also bring 35 down into like a mod 3 system. You can just do a cycle of 0, 1, and 2. And 35 would be equivalent to 2. And then you basically have what's the inverse of 2 in mod 3. And that would also be 2 because 2 times 2 is 4. And that gives you a remainder of 1. So either way, the inverse here is 2. And then for 21, we're doing this with mod 5. So we're going to do the same idea. We're looking for some number that is congruent to 1 mod 5. So this time we want the remainder when we divide by 5. So again, we can do this with trial and error. 21 times 1, so that's just 21 mod 5. So you take out 20 and you get a remainder of 1. So that's pretty straightforward. That's 1. So trial and error here is nice, but you can also, again, bring 21 into your cycle of mod 5. So 0, 1, 2, 3, 4. Because 5 mod 5 is 0. Because there's no remainder. And so, yeah, y equals 1 would, well, 21 would bring you to 1. And then 1 times 1 still gives you 1. So the inverse is 1 there. And then for 15 mod 7, we're looking for a number that when multiplied by 15, that's congruent to 1 mod 7. Again, we can do this with trial and error. Try out 1. That's fine. 15 times 1 is 15. Divided by 7 is 2, remaining 1. So we're good there. So the inverses aren't so bad for this one, but if needed, you can first just do like 15 mod 7, 21 mod 5, and 35 mod 3, and then find the inverses there. But the definition of an inverse is a number where when you multiply it by the thing that you're trying to find the inverse of, that you get something congruent to 1. Okay, I hope that makes sense. But these are the inverses here. And so now I think that's all the numbers that we need now. So we're just going to multiply these, and these, and then we're going to add them with order of operations. So multiplication first. 2. So let's get that. So we have 1 times 35 times 2. So that's just 1. So we have 70. We have 2 times 21 times 1 is, what, 42? The 1s make it nice because anything times 1 is itself, so that's fine. 3 times 15 is 45 times 1. And so this is what we're going to be adding together to get our answer. So, okay, so we just add those. So we basically write x is congruent to the sum of these, and you can write this as a general formula, like in summation notation. You could generalize this, right? So you could write like C1, C2, C3, and this part would be n divided by n1, n divided by n2, and n divided by n3, and then the corresponding inverses. So you could write like summation of each of those products, but we already did it here, so we don't need the general formula for now. This is just our general algorithm. And we get 157. So 70 plus 42 plus 45 is 157. got something too big. So what we're gonna have to do is simplify this down, subtract 105. I hope that this is right. So 157 minus 105, which is going to be congruent to 52. And that will be our actual final answer. So if you get, x is congruent to 157 mod 105, that's not wrong, but that's not exactly in standard form because this is outside of the range of numbers. So, of base numbers, if that makes sense. So, it's true if it's congruent to 52, it's going to be congruent to 157 mod 105. But, to keep it standard, it's better to write this answer. So, I need to check this. Let's make sure we actually got something that works. Let's see. So if our answer is 52, let's go back to these and see if 52 mod 3 is 1. So 52 divided by 3 is 3 goes into 5 once. 1 times 3 is 3. Subtract it, bring down the 2. 3 goes into 22 7 times, that's 21, and yes, that leaves me with the remainder of 1. So 52 would check for that. We're looking at the remainder, right? 52 divided by 5. So that one's more straightforward to divide out because we're going to get 10, which is going to give us 50. You can do that one step at a time if you want to, but that gives me a remainder of 2. So that checks out. And then 52 divided by 7. So 7 goes into 52 7 times. So that would be 49. And then D gives us a remainder of 3. So we're good. Wow, we actually did it. That's awesome. Okay, so technically we aren't sure that this is the correct solution overall, but we do know 52 works, so that's good. And if you want to kind of just check more answers, you can add 105 because this should work for as a general class of solution. So you can check 157 for instance for this, and keep adding 105. Check a couple of multiples of 105 added to this to make sure that it still satisfies this. But this is our overall solution. I'm pretty happy with it. I hope that makes sense. So let me just kind of run through the algorithm again. This was so scuffed, I'm so sorry. But people are being kind of noisy. I'm trying to write this out and calculate at the same time, so I hope that it's okay and nice and relaxing anyway. But the general idea is, step 1, have your system of congruences. Step 2, check that the moduli are all relatively prime or coprime. So between any two of the 3 or more, the only common factor should be 1. Okay, then next multiply them together to get a product. So your answer is going to be mod that number. Then you can kind of make this table, I suppose, or you can kind of do it all in one step, but just know you're doing different calculations at the same time. But write out the 1, 2, 3, or write out the congruence conditions, in a row. Then for the next part, you're multiplying the other 2 moduli, or another way of saying that is to take the product and divide by the modulus that you're on. So in this case, 105 is divided by 3 is 5 times 7, which is 35. So either you skip this inverse of, you should get something that's congruent to 1 mod, the one that you're looking at. Then we multiply all of those together, so the condition times the product times the inverse. So in this case we got 70, and so the condition is 2 times the product of the other 2 is 21 times the inverse is 1, so we got 42. 3 times 15 times 1 is 45, and then you add those together. In this case we got 157, but we're taking that mod of the product, remember? So mod 105, but because 157 is bigger than 105, rather 104, because it's 1 less, we go ahead and subtract a multiple from that to get 52. So x is congruent to 52 mod 105, and as long as we have an x that satisfies this, it should also satisfy this. So it's not just one answer, it's a group of answers or a class of answers, and that should work for this system of congruences. I hope this was interesting. Hopefully I can edit this up and put it all together for you. We can always come back and play around with this some